Coming to the speaker for today, we have Akshay Sarvesh here from Texas A&M University. And Akshay is a PhD candidate and a researcher in the Electrical and Computer Engineering Department at Texas A&M University, working in the domain of robotics. And over the course of his research so far, he has developed algorithms in the domain of motion planning, path planning, and dynamic control of robots in unstructured terrain using reinforcement learning based techniques and classical techniques. He's interested in the idea of different types of robots collaborating and cooperating with each other to fulfill a difficult task. And he's interested in collaborating with different researchers and is also looking forward to transitioning from his PhD to a more research-based role in the near future. So once again, welcome Akshay, and the stage is yours.
Thank you guys for the wonderful introduction. And I have to say that this is a great initiative. I really appreciate you guys coming together and having a platform for robotics researchers to just share ideas and views and upcoming research. I think it's very cool. I really hope that you get a lot more interesting people here and this keeps going forward. The title of the talk is going to be Path Planners and Controllers for Autonomous Navigation of Robots in Unstructured Domains. To begin with, I just want to introduce path planning. Why is autonomous navigation really important? We have firefighting, disaster relief, mining, reconnaissance survey. These are just some of the activities that are oftentimes viewed as harmful for humans. These activities can be quite fatal to humans as well. Oftentimes, we need robots to come in and perform firefighting or even go to the areas where humans cannot reach or perform a survey of the areas that are affected by disasters, for example. And mining as well. Mining is one domain which has adapted robots, autonomous robots, the most. It could be towards detecting methane gas leaks, or it could be towards detecting any other aspects of mining that could be viewed as poisonous or harmful to humans. Robots has its presence in mining today. Reconnaissance survey is something that's up quite a bit. What typically happens is when you're in an adversarial area, you tend to not want to send a human to perform specific missions. And in those types of missions, reconnaissance surveys, robots are very helpful. One common aspect of all these areas is the environment happens to be quite unstructured. It could be filled with negative obstacles that are something like potholes, or it could be obstacles where there are hills, or there could be even obstacles such as trees and shrubs. You cannot have one common algorithm for perception most of the times that can help you figure out how to navigate, that can give you a holistic view of the environment around you. What happens typically is you would, in this type of scenario, you would need to rely on your algorithm, rely on the acuity of your algorithm, the decision-taking capability of the algorithm to take you out of those tricky scenarios. But having motivated this problem, let me get to what path planning pipeline really is. There are path planning pipeline could be mentioned in two parts. I have perception and navigation. In perception, we have the robotic vehicle's state relative to its environment and mission, and that's obtained using proprioceptive and exteroceptive. And then the next part of path planning is navigation. In navigation, we have three parts: path planning, motion planning, and dynamic control. Path planning typically translates a higher level of autonomous mission to a desired path that the robotic vehicle typically follows. And with motion planning, the motion planning translates this desired path into motion primitives for the robotic vehicle. And the dynamic control, the motion primitives are translated to actuator commands, for example, acceleration or steering. To have a higher level mission that's dictated by humans, asking the robot to follow a certain set of waypoints, that could be the autonomous mission. and the global path could be the desired path. And then with motion planning, that desired path could be converted to motion primitives. Motion primitives could translate to anything like going straight, going left, going right, or whatever it is. And this motion primitives can then be translated to actuator commands. Actuator commands, for example, in the case of a differential drive robot, could be the difference in the wheel speed of the left wheel and difference in the wheel speed of the right wheel. This difference would lead to the robot turning either left or right. These are some aspects of navigation. Um, the work that I'm presenting today is going to be mostly in the domain of path planning, motion planning, and dynamic control. Uh, Talking a bit more about the work that I'm specifically presenting today, Global Path Planner, I want to say that there are two main approaches to path planning, two main general approaches to path planning. There are classical techniques and there are learning techniques. Some of the more important classical techniques happen to be potential field methods and active exploration methods like MPC. And with learning techniques, there are some techniques like learning to replace the entire navigation stack and learning navigation subsystems and or its components. Potential field methods, again, are a classical method. They've been present in the literature for quite some time. There are still some disadvantages in potential field methods. Oftentimes, they can get stuck in local minima. With active exploration methods, they're oftentimes computationally expensive, and their solutions usually work under some assumptions. With learning-based techniques, there oftentimes exists a lack of explainability and also a lack of repeatability. The path planning, again, can be global planning and local planning. Global planning could be, um, again, there are different ways of looking at this, but I'm calling PRM, RRT, RRT star, A star, and D star light as global planning because these are oftentimes a higher level plan, and these are oftentimes graph-based paradigms that come together to give you a final global plan. And with local planning are types of plans where you need a reactive, quick planning that needs to be done based on the sensor update that's happening. The local plans are also, local planning is also oftentimes done in higher speed. Potential field methods and active exploration methods like MPCs are another example of these types of local planning. Potential field methods are, again, like I said, potential field methods where the objective is to minimize a cost function. And in navigation, the cost function could be to minimize the distance between the goal and the current location of the robot. Active exploration methods also work on a similar context. They evaluate an objective function over a time horizon. And this is an example of a receding horizon controller. Um, with local planning, classical techniques, like I said, active exploration methods are computationally expensive. If I'm using an MPC and if I am actuating over an action space of, let's say, steering wheel and velocity, I have two action space, and depending on whether we are looking at a continuous domain or a discrete domain, it can get quite expensive in terms of a search space of O when square. And potential field methods can get stuck in local minima. And the solutions of potential field methods work in strict assumptions. And with learning-based techniques, like I mentioned, there's a lack of explainability sometimes, and also a lack of repeatability in some of the algorithms that we see. The question that we asked ourselves was, is it possible to overcome the disadvantages for navigating in unstructured terrains? That's what motivated us to get started with reshaping local path planner. Before getting into the heart of the algorithm, I want to define a couple of attributes. We have an operating region that we call omega OP. The operating region is two-dimensional. It has properties like height, surface friction, gradient, you name it, whatever it is. Operating region is just a region where the robot exists and the environment surrounding the robot. And this environment also contains the local path, and this environment could also contain the global path along with the obstacles themselves. The trajectory is defined as a sequence of endpoints, and we also have a set of trajectory. A desired global path that you can see in blue happens to be a part of the set of trajectories. The constraints that the global path come with is that oftentimes this global path can be stale, and oftentimes this global path can pass through obstacles. The idea here is that the global paths are generally unreliable. And we also have sensed environments that are sensed by our sensors like exteroceptive, proprioceptive sensors like LiDAR, camera, and so on. And obstacle points. Obstacle points are, in the way we are defining it, obstacle points would be a cluster of points that are close to each other. The idea is you want to avoid the obstacle space as much as possible. And local path. Finally, the local path is the path that the robotic vehicle takes. The reshaping local path planner algorithm, the idea is that it generates a local path such that the local path satisfies the constraints of avoiding obstacles as well as staying on the global path as much as possible. The idea here is that we have a cost of minimizing, and the cost happens to be path deviation. We want to minimize path deviation as much as possible. The input to the path planner happens to be an operating region, a sensed environment, a global plan, and the constraints are curvature constraints. Obviously, if we are talking about if you're talking about a vehicle like such as a Jeep Cherokee or a Ford F-150, it typically has a higher turning radius, which means that it has a lower, it has a higher turning radius, which means that it has a higher curvature as well. Sorry, hold on. What's the relation? It's the inverse relation. It has a lower curvature, which means it has a higher turning radius. And on the other hand, a differential drive robot, for example, like a ClearPath Moose or any other uh, similar footprint differential drive vehicle, could have a very small curvature and thereby having a higher radius of, which means that it can turn on its axis quite easily. That's one of the curvature constraints that we have. And we wanted reshaping local path planner to be platform agnostic. It should work on an Ackerman drive vehicle as well, and it should also work on a non-Ackerman drive vehicle as well, something like a differential drive vehicle. And we will demonstrate that. We have a demonstration video for you guys as well. And the output of this algorithm happens to be a local path that satisfies all these constraints. Let me also focus a bit more on PFMs and the issues with AEMs and PFMs. Again, with PFMs, the idea is that you minimize the distance, for example, that between the current location of the robot, as well as the final destination. This has a tendency of getting stuck in a local minima. A local minima could be viewed as something like this, where it is a false minima and depending on the curvature of the vehicle, if it gets stuck, if the robotic vehicle gets stuck in that local minima, come out. And that's a tricky situation to be in. It could result in stagnation of the robotic vehicle. And with AEMs, that is active exploration methods, like I already mentioned, if the actuation space for a 2D plant happens to be velocity and yaw rate, for example, the actuation space is going to be O(n square. It could be made efficient by discretizing, but it still is a bit expensive for real-time path planning. I want to talk about reshaping local path planner. What are the components of reshaping local path planner? To begin with, we have a hierarchical and a minimal action space. That is, we perform a constrained optimization to choose either left side or the right side. And this is depending on the overall cost. If the left side has a lower cost, we take the left side. If the right side has a lower cost, we go on the right side. And then we also have a synthetic vehicle rollout. Synthetic vehicle rollout is something like simulating your vehicle forward in time. You would try to simulate the vehicle forward in time by assuming some dynamics of the vehicle, and then you figure out if that path intersects with an obstacle. If not, you would perform reshaping. I will get to that as well. And then we also have another unique aspect called a path-aware turning moment field. Path-aware turning moment field is inspired from the potential field techniques, but in this case, we call it path-aware turning moment field because there are a few components to it. We have a path following moment, and we have a path-aware turning moment from obstacles that are blocking, and we have a path-aware turning moment from obstacles that are non-blocking. These three aspects come together and make sure that the disadvantages of potential field methods do not creep in. Synthetic vehicle rollout is again very similar to what we see in receding horizon controller, where we simulate the movement of a robotic vehicle for, let's say, n time steps, for k discrete time steps in real time. As you can see, this is very similar to receding horizon controller, where we simulate the action for 4 time steps and we take the first action. This is the first part of the algorithm, and the second part of the algorithm is a path-aware turning moment. But first, let's look at path-agnostic turning moment field. With a path-agnostic turning moment field, as we see in the context of potential field methods, there exists this region where we call it a dead zone. We call it a dead zone because the influences from the obstacle cancel out each other. These influences, after getting canceled out, creates this channel that tell the algorithm that there are no obstacles here. It tells you that it's all A-okay, it's all green to go, it's all good to go along this path, but it turns out that it's not the best path. This is what happens when we look at a path-agnostic turning moment field. But when we look at a path-aware turning moment field, again, I will get to what it really means. We can see that the influence of these obstacles starts much earlier, and thus enabling collision avoidance and also thus preventing the stagnation of the vehicle. This is also a very important attribute in making reshaping local path planner avoid obstacles. And finally, also, let me talk a bit about the hierarchical minimal action space. The actuation space of the synthetic vehicle, like I said, is set to a binary decision. It's either left or right in a 2D context, and we choose left for arbitrarily breaking ties. I do not want to get a whole lot into the mathematical details of the algorithm, but I just want to touch upon briefly as to what it is. We have 2 types of moment, a path following moment and a path aware turning moment. The path following moment is inspired from the pure pursuit controller, where the robotic vehicle tries to follow the path as closely as possible. And path aware turning moment is inspired from um, the obstacles that are present, and it's considers the moment that's coming from the obstacles that are present on the path, and it avoids those obstacles as much as possible. I will get to that a bit more in detail as well. And then we also have a total turning moment that respects curvature constraints. We have a filter here, a filter that's respecting curvature constraints as well. And finally, this is just a very simple Euler integration technique for simulating the synthetic vehicle rollout. In here, we set the second derivative of the heading angle to be the overall turning moment that we get from the path following moment as well as the path aware turning moment. As you can see, the MR, that is the total moment, feeds into the moment filter where it's constrained to the curvature. And that moment filter is again fed into the synthetic vehicle rollout, the algorithm where the second derivative of the heading angle is set to the moment, and thereby the robotic vehicle knows which direction to turn based on the obstacles that are present. Again, without getting into a whole lot of detail about the math, this is a synthetic kinematic model, a very simple kinematic model that we have right now that just does Euler integration. The initial conditions of the synthetic vehicle are synchronized with the current location of the vehicle. And a path following moment is also something that is, like I said, it's inspired from the pure pursuit algorithm. This is a turning moment. And again, this is a type of moment that can be tuned based on lambda1 and lambda2. This could be based on the environment we are in, and this could also be based on the type of the vehicle that's being driven. Before getting into the obstacle avoidance moment, I just want to briefly touch upon the obstacles. How do we define the obstacles? We define a blocking region. A blocking region is a region where the obstacles are present quite close to the local plan. And the idea is you want to not have any obstacles in the blocking region. And we also have obstacles that are in the non-blocking region. For example, the obstacles that are in yellow and the obstacles that are in green. These are obstacles that are right of the path, and there are obstacles that are left of the path. And finally, we also have obstacles that are present in the ignore region. What this means is these obstacles can be ignored. You need not compute. You need not waste your precious computation resource on figuring out if these obstacles contribute to avoiding collision or not. The idea is that the reshaping local path planner algorithm tries to make this set of obstacles that are blocking null. Without getting into a whole lot of detail about the math, I briefly want to touch upon the influence function, that is the moment function. The moment function has a relation, it's a piecewise linear function to begin with. It has a relation like this, where if, let's say, the obstacle is very close to the robotic vehicle, then the moment is going to be experienced as a single variable as a2. It's a step function. It is a completely linear value of a2. And if, let's say, it's in a region of a1 to a4, the the moment that the obstacle produces drops with an exponentially decreasing relation. And then we also calculate the moment that's coming in from all the obstacles that are in the blocking region, that are in the non-blocking region in this context. With blocking obstacles, it is a bit more nuanced. What we do with the blocking obstacle is we consider moments that are along the path, and we call that IBP of LP. The moment relation looks very similar to the previous equation that we saw here, um, but we consider moment in 2 dimensions, that is along the path and also perpendicular to the path. That is, we assume the presence of a cross-track error as well. These two moments, we feel, is what gives us the ability to overcome the disadvantages of potential field techniques. Again, we also introduce the binary decision variable here. That is, you either want to swing left or you want to go right, depending on what type of obstacle is present and depending on the type of the cost that you're trying to minimize. Finally, the overall turning moment that is related to obstacles, that is considering obstacles that are not blocking and considering obstacles that are blocking, is given by MO equals MO non-blocking plus MO blocking. That is, we just add the moment that's coming from the obstacles. And then finally, I just want to come back to this slide again, which captures the logic of the algorithm. That is, we have the overall moment, that is the sum of the obstacle avoidance moment and a path following moment. We call the obstacle avoidance moment also the path aware turning moment. We also saw a view of how it looks, and we pass that to a filter which constrains the curvature and figures out the right moment that it can take based on the curvature. And also we finally pass this moment into our Euler integration technique, where we set the second derivative of the heading angle to be equal to the filtered turning moment. Let's look at some of the scenarios where potential field methods fail, but reshaping local path planner can succeed. This is a scenario potential field methods can oftentimes fail because it fails to recognize the presence of obstacles on either sides of a U channel. Reshaping local path planner, as you can see, comes ahead and figures out that there exists this potential for getting stuck and gets out, thereby figuring out a path that's also curvature constrained based on the dynamics of the vehicle. Usually the local path is much more shorter than the global path. That's to avoid computation time. That's to minimize computation time and also take a fast action as much as possible. We can also see thinner lines that represent instantaneous path reshapes as the vehicle moves. Let's look at another scenario that is a bit more complicated. This is a more complicated scenario that is constructed that includes multiple dead ends and miscues. The global path, as you can see, is encroaching into the obstacles. It is again observed that the actual vehicle successfully negotiates the path based on the reshaping local path planner. As you can see, these are the instantaneous path reshapes that had to be done before reshaping local path planner figured out the most optimal scenario. In this scenario, the robotic vehicle is starting away from the global path as well. We can see a few more scenarios where the reshaping local path planner successfully avoids obstacles along the global path. Let me also show you a scenario of dynamic obstacles. What happens when there are dynamic obstacles present in the obstacle avoidance scenario that we're trying to build? This is a scenario where the obstacle is moving from left to right. This is at t is equal to 0, and then it moves until t equals 7.5. But right after t equals 7.5 becomes static. This is one of the scenarios that we saw in the previous case. As you can see, the reshaping local path planner works in this case as well. But obviously, to account for um, change in the obstacle constraints and change in the computation time, it would make sense to reduce the length of the local path when we are dealing with dynamic obstacles, just to avoid um, spending a whole lot of time computing. And finally, we also performed some real world experiments. And some of the robotic vehicles that we used to perform the real world experiments are these. That is, we have a ClearPath Moose and a Jeep Cherokee. The environment where we performed the experiments were at Rellis campus, which is at Texas A&M University, which is 10 miles away from Texas A&M University. This happens to be a retired quarry area, which is like a prairie grassland with obstacles such as trees, and the general terrain is quite bumpy and not a very pleasing place to drive. Sorry, I don't know. Okay, fine. Okay. The robotic vehicles that we have happen to be a Jeep Cherokee and a ClearPath Moose. Let me increase the speed. As you can see in this scenario, the global path passes through the obstacles completely, and the ClearPath Moose avoids striking the obstacles based on reshaping local path planner algorithm. And this is another scenario where the robotic vehicle was oriented away from the global path. It first reorients itself and then tries to avoid the obstacles successfully. Again, this is a scenario where the global path is going through the obstacles in such a way that the robot maneuver itself in between these two trees, and it successfully does that. And in the final scenario, we are looking at how Jeep Cherokee behaves in this environment. Okay, these are some of the experiments that we had planned. Let me get to, sorry, the next part of the presentation, the final part of the presentation, where I just want to briefly touch upon reshaping viscoelastic string-based path planner. Before getting to this, I just want to know if we're doing okay on time.
We still have maybe like 10 minutes for the presentation, and so that like we can get another 50 minutes for the discussion.
Okay, got it. Yeah, I think I have it such that it gets over in another 10 minutes. Okay. And the second part of my research happens to be reshaping viscoelastic string-based path planner. This is joined to work with Sarvesh, who's currently a grad student at University of Michigan, and also my advisor, Dr. Gopal Swami. The idea here is that given a global path, with a series of discrete points, we model the global path as a viscoelastic string. That is, we model the global path as containing a string and a damper, a string mass damper system. We approximate the path to be this system. And we also assume the presence of anchor points that tether the original global path, such that the anchor points keep the original shape of the global plan. The idea here is that the presence of these tether anchor points ensures the curvature constraints. That is, you don't want to deviate a bit too much from the curvature constraints. The idea here is quite simple. Given a global path, there are obstacles. Again, we assume the presence of reshaping forces, path reshaping forces coming emanating from the obstacles. How would the obstacle reshape itself such that it avoids striking the obstacles and such that the robotic vehicle can successfully negotiate the path? This is an approximation that we make by assuming the path to be consistent or path to be containing springs, masses, and dampers. The path again is the path points again are simulated by this equation right here. Again, I don't want to get a whole lot into the math here. The ODE that describes the motion of the path is described here. We saw that in the previous slide. The path force is again given by this equation here, which is inspired by the spring spring relation, the linear spring relation. And finally, the obstacle moment is the obstacle force or the obstacle moment is also inspired from the reshaping local path planner, where we have a force emanating from obstacles that looks like this. We have a initial linear region of force where the obstacle exists within a certain region, and that force happens to be A2. And as the obstacle moves away, the force drops. The force that the obstacle sees drops linearly. The path force enables the robotic vehicle to move along the path, and the obstacle force reshapes the path such that path or the string such that a new path is created such that it avoids the obstacle. And again, this is how the obstacle force looks. It is initially quite high, and then it starts decreasing radially as the distance increases. And after reaching a point, we have again a thresholding filter where it wouldn't even matter. The force coming from the obstacle wouldn't even matter anymore. We again want to compare this with reshaping local path planner. As you can see, the reshaping local path planner output looks something like this, as we see in red, and the reshaping viscoelastic string path planner looks something in looks like the output as we see in the pink. You can see here that the reshaping viscoelastic string path planner performs slightly better than reshaping local path planner in terms of sheer cross-track error. We compare this with a few other scenarios as well. Reshaping local path planner again is quite equivalent by the looks of it, but if you look at the cross-track error, if we look at the actual cross-track error of this scenario, reshaping viscoelastic string path planner has a lower cross-track error. And another scenario where, again, reshaping viscoelastic string path planner has a better edge over reshaping local path planner. Obviously, these are based on the footprint of the vehicles themselves, also based on tuning parameters themselves. With the number of tuning parameters that are present in the reshaping local path planner, it can oftentimes get a bit difficult to transition between vehicles of different footprints. Their reshaping viscoelastic string path planner might come in and take the slack. One of the other disadvantages of reshaping viscoelastic string path planner happens to be that we are solving a differential equation. It turns out that it is quite expensive doing it online in real time. For most of online real-time scenarios, we prefer using reshaping local path planner. This brings me to the end of my presentation. I want to leave the floor open for any questions or discussions or any ideas that you guys might have.
Thanks, Akshay, for presenting your work, and it was very interesting to see the algorithm also like tested in the real-time scenarios, and you explained your work with a good amount of details. Now we have the time for 2 or 3 questions maximum from the audience.
What would you say is the most difficult part about doing the field testing?
Thank you for your question, Mike. During field testing, there are a number of difficult aspects to deal with. One of them is the heat in Texas. If you're performing this field experiment, say in the middle of Texas summer, it becomes very tricky. It gets very hot, it gets very humid. And there is something nice to seeing your algorithm work in simulation. But the moment you take it to real robots, things start failing. And it is quite difficult to get it working in the real robot. Um, and there's also other constraints like managing your schedule and managing the schedule of the people around you. It is overall a different ball game um, dealing with an experiment in a real world scenario. But yeah, it was definitely quite cherishing, and I had help from my teammate in this project, Austin Carroll, who was also quite good in dealing with field robotics. But yeah, it is a different type of beast to deal with um, in working in the field. Things can oftentimes go wrong, and your sensors stop working in the Texan heat. um, some package could be missing and you do not have internet to download a specific package. So it's quite nice. It is definitely something that's quite cherishing for me.
So are there any plans to develop these algorithms further? And if so, what are the areas that you want to focus for
Yes,
improvement? Yeah.
that's a very nice question. I wish I had more slides to explain the ongoing research in that area, which I'm still working on. I mentioned vehicles of different footprints. I also mentioned that reshaping local path planner is vehicle agnostic, vehicle footprint agnostic. It so happens that tuning these parameters when we transition from a differential drive vehicle like a ClearPath Moose. Sorry, let me go back and show you these vehicles here. Yeah, transitioning from ClearPath Moose to a Jeep Cherokee is a bit tricky because the loading constraints are quite different and the dynamics of the vehicle itself are quite different. ClearPath Moose happens to be a differential drive vehicle and is capable of turning along its axis. It almost has a radius of curvature that is um, quite low. And Jeep Cherokee, on the other hand, has a higher radius of curvature. Um, and also the environments themselves, depending on the type of the environment we are in, um, there exists different tuning parameters that has to be tuned. For example, some of the parameters that I spoke of in terms of path following moment, lambda 1 and lambda 2, they have to be tuned. What we are investigating right now is the use of reinforcement learning algorithm to figure out what is the optimal policy that can figure out these parameters themselves. This is something that's ongoing. This is something that we are currently working on in the context of reshaping local path planner and reshaping viscoelastic string planner right now. And we feel like these techniques could be quite powerful in transitioning between different vehicles, and it could save that precious time in tuning your parameters.
Okay, great. I just have one more question. While testing it out in the real scenarios, have you also done testing it with moving obstacles?
No, we did not test that with moving obstacles. The area that we were performing the test at, I don't think we had the requisite permission to test with dynamic obstacles to begin with. We've not tested definitely, but the reason why this slide was added and this work was even done was when we submitted the journal to RAL. One of the comments that we received was the algorithms. Okay, it's good, but what happens if we are looking at dynamic obstacles? What happens if we are looking at dynamic obstacles? And we were only able to simulate the dynamic obstacles, and we did not have enough time to go out again in the real world and perform this experiment with dynamic obstacles. And so oftentimes the permissions that you need to perform these types of experiments could also be a bit trickier to obtain.
So we have reached the end of the session today, and let me conclude by thanking Akshay once again for presenting his work and also sharing his insights about the improvement of this kind of algorithms as well. Thank you, Akshay.
Yeah, thanks a lot, guys. I think this is a great initiative. I'd love to get in touch with any of the participants here. If you want to talk about this, please send me an email. and we can get on a Zoom call. It would be great to chat and get different perspectives on this. Also, I'd love to know about your research as well. It would be quite nice to see where this goes.
Definitely. Thanks everyone for joining today's session. On the 59th session on 17th of May, we have Sarath Sridharan from Colorado State University presenting his talk on the topic of human-aware AI, a foundational framework for human AI interaction. See you all again for the next session. Thank you.